Okay, let's talk about a word that I know sounds super complicated, stoichiometry. But here's the secret. It's actually the most powerful tool a chemist has. Seriously, think of it as the ultimate recipe for any chemical reaction. It's what turns chemistry from just messy guesswork into a real predictive science.
I mean, have you ever wondered about that? How can someone mix two clear liquids together and know with certainty that they're going to produce exactly 10 grams of a white powder? It's not magic, not at all. It's stoichiometry. This is the stuff that lets us predict the future, at least in a test tube.
You can think of it like this. It's like a building plan for a porch. The plan tells you, for every single porch, you need exactly 4 posts and 16 floorboards. You can't just throw some wood together and hope for the best, right? Well, a balanced chemical equation is the exact same thing, but for atoms and molecules. It is the blueprint. It's the non-negotiable set of instructions that tells you the correct proportions for everything.
So here's our game plan. First up, we're going to learn how to read the chemical recipe. That's the balanced equation. Then we'll get into the secret ingredient that makes it all click, the mole. After that, we'll actually build our conversion bridge and use it to solve a real problem. And finally, we'll take a look at what happens when our perfect theory crashes into messy, real-world lab work.
All right, let's dive into Section 1, the chemical recipe. You know, before you can start cooking anything, you have to make sure your recipe is written down correctly. In chemistry, that means balancing the books. We have to make sure our equation is spot on before we even think about starting.
This all boils down to one of the most fundamental laws of the universe, the law of conservation of mass. It basically says you can't just create or destroy atoms in a reaction. You can only rearrange them into new combinations. So when we balance an equation, all we're really doing is some careful accounting, making sure every single atom we start with is still there at the very end.
Okay, let's look at a classic example, iron rusting. On the left, you see the unbalanced equation. And, well, that just can't be right. It's like saying 1 iron atom goes in and magically 2 pop out. No way. But now look at the balanced version on the right. See those big numbers we added in front? Those are called coefficients. Now we have 4 iron atoms and 6 oxygen atoms on both sides of that arrow. The books are balanced. Now we have a recipe we can actually use.
So if the balanced equation is our recipe, what's our universal measuring cup? We can't really use grams because different atoms have wildly different weights. So the secret ingredient, the thing that lets us actually count atoms and compare them, is the mole. Don't let the name scare you. It's just a word for a very specific, very large number. Think of it like a chemist's version of a dozen. It's how we compare apples to apples.
And this right here brings us to the absolute heart and soul of stoichiometry, the mole ratio. It's just a simple fraction that we pull directly from those big numbers, the coefficients, in our balanced equation. This little fraction, it's the magic key. It lets us convert from the amount of something we have to the amount of something we want to find. And look how useful this is. Let's take the Haber process, which is how we make ammonia. From this one single equation, we can write a ratio to connect any 2 things in there. We can relate nitrogen to hydrogen, or hydrogen to ammonia, or nitrogen to ammonia. And since you can flip every ratio upside down, that gives us 6 possible conversion factors, all from one simple balanced equation. It's incredibly versatile.
Now, pay attention, because this is the single biggest mistake people make. You cannot, and I mean ever, compare the grams of one substance directly to the grams of another. It just doesn't work. That chemical recipe we've been talking about, it's written in the language of moles, the language of counting particles. To use it right, you absolutely must convert to moles first. No shortcuts.
Okay, so we've got our balanced recipe. We know our secret ingredient is the mole. So now let's actually build the process, the super reliable bridge that's going to take us from a quantity we know to a quantity we need to find in any problem.
Okay, if you remember one thing, just one thing from all of this, let it be this mantra. Say it with me. Grams to moles to grams. That's it. That's the path. That is the bridge that will get you across pretty much every single mass-based stoichiometry problem you're ever going to face. It is your foolproof guide. Seriously, tattoo it on your brain.
So here's that journey in 3 simple steps. Step 1. You take the mass of the stuff you're given and you convert it into moles using its molar mass. Step 2. This is where you cross the bridge. You use that mole ratio from our balanced equation to find the moles of the stuff you're trying to find. And finally, step 3. You take the moles of that new substance and convert it back into mass using its molar mass. That's the whole game right there.
All right, enough theory. You know, the best way to really understand the bridge is to just walk across it. So, let's take this exact 3-step process and apply it to a real problem, the kind of thing you definitely see on an exam.
Okay, here's a problem from a practice test. We're given 27 grams of aluminum, and we're asked to figure out the mass of hydrogen gas that's going to be produced. The equation is already balanced for us, which is nice. So our given is aluminum, and our unknown is hydrogen. Time to walk the path. Grams to moles to grams. Let's do it.
First step, grams to moles. We're starting with our 27 grams of aluminum. To get this into moles, we just need to divide by its molar mass, which you can find on the periodic table. For aluminum, it's about 27 grams for every mole. And hey, the math here is pretty easy. 27 divided by 27 gives us exactly 1 mole of aluminum to start with. Step 1, done.
Okay, now for the most important part, crossing the bridge. Moles to moles. We look back at our balanced equation, see that 3 in front of the hydrogen and the 2 in front of the aluminum? That's our mole ratio. It tells us that for every 2 moles of aluminum we use, we make 3 moles of hydrogen. So we take our 1 mole of aluminum and multiply it by that ratio, 3/2, and that tells us we're going to produce 1.5 moles of hydrogen gas.
We're on the other side of the bridge. Final step, moles back to grams. We know we have 1.5 moles of hydrogen gas, which is H2. Now, the molar mass of a single hydrogen atom is about 1. So for H2, it's 2 grams per mole. We multiply our 1.5 moles by 2 grams per mole. The moles unit cancels out, and we're left with our final answer in grams.
And there it is, 3.0 grams of hydrogen. See? By just sticking to that path, grams to moles to moles to grams, we were able to find the solution without any guesswork. It's a process, and it's a process that works every single time.
So that was a perfect calculation, on paper where everything works out just right. But chemistry in the real world, well, let's just say it can be a little bit messier. So let's talk about the difference between what our perfect recipe predicts and what we actually get in the lab.
That number we just calculated, the 3.0 grams, that's called the theoretical yield. It's the absolute maximum, perfect world result. But the actual yield is what you physically weigh on a scale after you've done the experiment. And, it's almost always a little bit less, thanks to things like side reactions, or maybe you just spilled a little bit while transferring it. It happens.
So to kind of grade their own performance, chemists calculate something called the percent yield. It's super simple. You just divide what you actually got by what you should have gotten and multiply by 100. For a simple reaction, getting over 90% is great. But for a really complicated multi-step process, even a 40% yield might be a huge success worth celebrating.
Okay, before we finish up, let's just quickly review the biggest traps to avoid. Number 1, always balance that equation first. It's the foundation for everything. 2, never, ever use mass ratios. It's a mole world. 3, don't round your numbers until the very, very end, or you'll get small errors. And 4, it sounds obvious, but double check that you're using the right molar mass. Avoiding these common mistakes will save you so much trouble. So there you have it. We've mastered the chemical recipe. You now know how to read the blueprint and predict exactly what's going to happen. But this brings up a really interesting new question. What happens in your recipe if you have enough flour to make, say, 20 cookies, but you only have enough chocolate chips for 10? What happens when one of your ingredients runs out first? Well, that, my friends, is the concept of a limiting reactant, and it's exactly where we're going to pick things up next time.